Yes, hello. Professor, before we begin, I want to clarify two quick points. First, are you willing to answer all my questions that I've provided today, and do you have enough time to go through them?
How much time do you need?
Um, just as much as you're willing to provide. That will do for me.
15 minutes should be good. Go ahead.
Okay. Second, I want to express how grateful I am that you're taking the time to speak with a young engineering enthusiast and assisting me with my writing project. I'm busy. I'm busy. I'm talking to a college dean. A college dean. I'm doing an interview, mom. I'm sorry. Hello. Sorry. Yeah, I cut out for a second there. Um,
I'm still here.
okay. I also like to note that this call is being recorded. I want to make sure I have your consent for that.
You are free to record the call.
Okay. Thank you. I promise the formalities are almost over. Uh, this is for my paper. Have to recap your credentials. And just to make sure I have everything correct, you're currently serving as the chair of the Daniel Guggenheim School of Engineering at Georgia Tech, aerospace engineering to be specific. And previously, you served as the associate dean for academic affairs at the same institution. And also, you are the founder of the High Power Electric Propulsion Laboratory that was established in about 2005. Is all that correct?
That is all correct.
Okay. All right, moving on to the interview questions themselves. In your view, which propulsion limitation, specific impulse, fuel mass ratio, or engine efficiency poses the greatest barrier to human deep space travel, and why?
Well, it counts on where the humans are trying to go. Where are they trying to go?
For the purpose of this paper, I would like to research beyond the moon. Really, that's the field that we're going with.
Is that Mars or somewhere else?
Um, it could be Mars, but just do you want me to be more specific? Or
Yeah, it starts to impact the answer.
okay, yes. So yes, Mars. Hypothetically speaking, yes, Mars.
So the challenge with taking humans anywhere is that they have an expiration clock because they require not only to move their mass, but you have to take a life support system and you have to take all of their consumables, right? Oxygen, water, food, which drives up the mass of the entire system you're trying to move. So two things become critical there, and then sometimes they actually fight each other. Number one, you want a high performance engine in terms of thrust. That way you can get up to speed rapidly, so you can get the humans where they need to be before they use up all their consumables. But at the same time, you want incredibly high performance in terms of efficiency so that you can minimize the amount of fuel it takes just so you can get all the payload there. Now, historically, chemical propulsion is best for high thrust. However, it has very low fuel efficiency. Electric propulsion is great for fuel efficiency, but it has very low thrust, or at least you need a lot of electrical power to do it. And so when you're dealing with humans, those two things are fighting each other, right? You want a lot of efficiency so you can take the humans and all their consumables, but you need to do it quickly. Am I answering your question?
Yes, you are. You're doing quite well at it. Yes. Um, all right. Move. We like to elaborate more on the first one, or do we like to move on to the second one?
Let's go on to the second one.
Okay. How do current chemical propulsion systems compare to emerging alternatives like nuclear thermal, nuclear electric, or solar electric propulsion in terms of feasibility for crewed missions?
So current chemical propulsion systems, let's call state of the art, where you can safely do it, hydrogen, oxygen, you can get up around 460, 470 seconds ISP. That's fuel efficiency. If you go nuclear, you have two options. You can do nuclear electric, that is, you turn the heat on the nuclear reactor into electricity with your favorite cycle, Brayton, Stirling, whatever, and then you use that electricity to drive some high power electric propulsion system, all thrusters, ion engines, MPD thrusters, whatever. The other version is nuclear thermal propulsion. And what you do there is instead of having, smoke and fire inside the rocket engine, you just take the fuel, you flow it over this really hot nuclear reactor, and then you get, 1,000+ seconds of specific impulse. So you get both the higher performance and the higher efficiency, with a higher thrust. With respect to flying people, one, you have to get through the launch issue of like, do we trust that we can launch this thing, and if it explodes, it's not going to blow nuclear particles all over Florida and kill everybody. That's hurdle one. The second one is no one has ever flown, full-scale nuclear electric, right, where they're turning nuclear power to electricity at hundreds of kilowatts of power, and no one has ever actually done a nuclear thermal rocket on orbit. So I would say the probability of either is probably pretty similar, just because no one has ever done it. You could help me out with the answer if you want to go in a particular direction.
No, I think you've answered it quite nicely. Moving on. Question number 3. What are the most significant engineering challenges in designing radiation shielding that is both effective and lightweight enough for long duration missions?
It's typically it deals with the mass of the shielding, right? Water, based on what radiation you're trying to block. Typically, water or lead are great alternatives. There are other things, but they just tend to be dense, right? Because of the radiation you're trying to stop, and the mass goes through the roof. So there are a lot of configurations where people will just put up shielding on one half of it and let the other half, radiate out of the backside of the vehicle so they can light it up. But it's tricky. And the other piece that you haven't asked about is both nuclear thermal and nuclear electric. The reactor gets really hot, and so now you have to build these big radiators to keep the thing cool so it doesn't melt down the structure. And in space, the one way we have to cool is through radiation. We don't have convection or conduction anything. So the radiator gets really big, it gets really heavy, which hurts the performance of the overall rocket because you're hauling around a bunch of radiators instead of fuel and people or cargo.
Understood. Question 4. From a materials science perspective, which spacecraft components are most valuable to a long-term duration from cosmic rays, thermal cycling, and micrometeoric impacts? Sorry, not valuable. Vulnerable.
Well, they all are. When you build an engineering system of that scale, it all has to work. So I wouldn't. If you break any one of those, the system is going to have an issue, where the mission's not going to be successful. So I wouldn't say it's like. I wouldn't say that there's one that you could just neglect. They all have to work. I would probably say the one that we know the least about, if I can phrase it that way, is to run nuclear thermal rockets. You're asking for the fission material to run really, really hot, and it will. The problem is all of our experience with those hot nuclear materials are for fusion reactors for generating electricity, right? Nuclear power plants. But those power plants run those nuclear reactors at much, much lower temperatures, so the materials don't really get that hot because they're typically just boiling water, so they don't get extremely hot. In a nuclear thermal rocket, you're going to ask it to run much, much, much hotter than you would on something for the ground so that you can run the rocket. We don't have a lot of experience and data running those fission materials as hot as you would need to have a good nuclear thermal rocket. So there's some space there where we can do more research. And the others as well, but I would think that's, if I had to say where there's one of them that needs the most work, and I say that loosely, it would probably be on the nuclear fission materials or nuclear thermal rockets.
Understood.
And I'm not saying that we can't do it. I'm just saying there's work to do.
Understood. All right. Question number 5.
And this pause. I want to go back to that. The second issue is there are a lot of security issues around working with that material. So not just anyone's going to have access to that material to be able to do that kind of work. Okay, go ahead.
Yes. Question number 5. How accurately can engineers currently predict the failure rates of critical spacecraft systems over multi-year missions, and what uncertainties remain in those models?
That's a big question, so I'll go back a little bit. So with any of this hardware, we typically test it on the ground to as close as we can how it's going to operate in orbit. And so we can understand that engineering-wise, will the design operate on orbit as planned? And typically all the stuff we run, if you need to run it for a year on orbit, you have to demonstrate it will work for a year and a half on the ground. That's NASA's metric. That way, when it goes up, everyone is very confident that engineering and design is going to work. The problem is you now have to manufacture it. And when you manufacture it, there are tolerances. And then someone has to assemble it and put it into a bigger system. And there are just all these little chances for errors. We have gotten pretty good about building things that you can only put together one way. We've done pretty well about doing checkouts to make sure the system works as designed. None of it's 100%, but you should be thinking high 90s for most things that we do. They're not cheap, but we do a pretty good job of making sure stuff is going to work. But it gets expensive.
Understood. Question number 6. What achievements in self-healing materials compromises or excuse me, of coatings. Sorry, let me repeat it. What achievements in self-healing materials coatings show the most promise for improving spacecraft durability beyond low Earth orbit?
That's a big question. I don't have enough information to answer that one.
Understood. All right, move on to question number 7. How do you evaluate the trade-off between mission duration and crew health risk, especially regarding radiation exposure, microgravity effects, and psychological stress?
So, I mean, you're mixing in things where I'm not an expert. I'm not an expert in human health or human psychology. It counts on who's doing it. Historically, we've always treated, let's say NASA, treated space flight as something where the people are going to go up and they're going to come back safely. And so when you say that, you're putting lots of limits on the mission because you're saying I'm not going to hurt them at any point and I'm not going to do irreparable damage to them. I'm not going to take them past any radiation limits or any of these things, right? You're actually making a lot of engineering constraints on the system because you're saying you're going to bring them back safely. It's not clear that some of the stuff that's happening in private industry, that some of these trips will be one way.
Understood.
There will be no expectation of bringing the person back, which is a different discussion of how you design the system. So, to answer your question, right, you have to put more metrics on it. Let's say more boundaries on it.
Could you speak more about the microgravity effects? Maybe more on the engineering side of things.
So we have quite a bit of experience with microgravity. Are you talking about how it impacts people or the hardware?
Well, when you design the hardware, I reckon you have to take the people into account, and so I would say more on the hardware side because it does affect the person, if I'm correct.
Well, I'm going to pull those two things apart. For the hardware and microgravity, we do a pretty good job of either simulating it on the ground or flying the stuff early and often to figure out how it's going to work in microgravity. So we typically don't have lots of issues of, oh no, it's a microgravity and now it doesn't work. We sorted out a lot of that stuff. For the people, we have a subset of data from how people have flown to space over the decades. I'm not a health expert, but there are people who are experts on those topics, and you probably have to talk to them on what the limits are.
Thank you for your honesty. Moving on to question 8. To what extent do you believe current life support systems could be scaled or redesigned to operate reliably for multi-year missions without resupply?
So once again, I'm not a life support expert person. You would have to talk to them. Clearly, we know how to make life support systems. Clearly, the International Space Station has been up there decades. Clearly, they created a system that they can repair and keep humans going. But I'm just not an expert in that area, so I'm not going to make up something for you.
Thank you once more for your honesty. Question number 9. Some argue that deep space travel is already possible if society itself accepts a higher level of risk. From an engineering standpoint, what risk do you consider unacceptable for a human mission beyond the moon?
Well, it's not an engineering standpoint. It's what do people want, right? I'll say it differently. If you get on your bicycle, you are accepting an extraordinary amount of risk. If you don't fall, you'll get hurt, right? Or you'll break an arm or something.
Mm.
However, if you get in a car, you have a much higher demand on your safety, right? You can run into a car with a lot. You can run into a car pretty fast. You can be in a car, it can hit something going relatively fast, and you have a high expectation that you're going to walk away from that. And that's not a requirement that you have on a bicycle. But you're making a decision when you get on a bicycle or roller skates or an electric scooter or a moped or a motorcycle that you're going to take all this risk on. And when you get in a car, you're saying, I won't take all the risk. So it's not really an engineering decision. It's a person's decision of like, I will fly on this if you can give me this level of risk. And different people have different amounts. In our society, we have said that if you can sell cars, the car will be this safe, or you cannot sell it. We've said that if you build airplanes that are going to fly people around, the airplane will be this safe, or we're not going to let you fly people on it. It's a government standard that has been implemented. For spaceflight, that has not been sorted out yet. Your question was, we can fly to deep space right now. People just have to be able to accept more risk. We can go into space and we can go some distance. You'd have to define what you mean by deep space, but we can go some distance in space with people.
So just to clarify your point, you're saying that at the moment, exploration into space and the risk associated with it is purely relative because there's no government standard. And to clarify what I mean by deep space, again, just to Mars, or just around, just to Mars, and generally speaking, beyond the moon.
I'll put a little more with it. You can engineer a system to give you any level of safety that you'd like when you go fly into deep space. The question is, can you afford it? Just financially, it's going to be a big system with a lot of testing and a lot of safety in it and redundancy. And you may not even want to purchase it when you find out what the sticker price is.
This is a side question, but is most of the challenges with space exploration just cost?
To first order, if you said one-way trip to Mars, we have engineering solutions where we can send people on a one-way trip to Mars. Then if you said, well, one-way trip and 90% chance that they make it, well, that's a slightly, that nothing breaks before they get there. That's a slightly different system, costs more. And then you said, well, 95% chance that they don't die on the way there from something breaking, and you can keep them alive for 1 month once they get there. That's another system, a lot more expensive. So those things, we can do those things. And even if you were like, oh, well, I want to come back, well, you could buy more spacecraft and you could position them at Mars already and to bring you back. It's just you'd have to pay for it, and it starts getting pretty expensive. So up into, something like Mars, we could absolutely take a person to Mars. Probability of them living the whole time and all that, it's questionable, but there's no physics limitation for us doing some things. If you start going farther than Mars, then we start running out of technology to pull it off in a human lifetime.
All right. Final question, question number 10. Looking ahead, 20 to 35 years roughly, which technological breakthroughs do you believe are most essential for making human deep space travel safe, sustainable, and scientifically productive? And deep space meaning just Mars.
That's a lot of crystal ball there. Because you just never know what's going to happen. I think there are some advances in power in space, be it nuclear, be it solar. If we have advances in available power in space, we're going to be able to do a lot more.
Is there anything, any particular technologies that you have hope for that is in early development that you believe could extremely help people to explore deep space?
Just what I said, power, either solar power or nuclear power or whatever. If you have more power, you have the ability to do more things or go faster.
All right. Well, Professor Professor, this concludes the interview. Is there any leaving comments you would like to give me?
Good luck with your project. Enjoyed the conversation.
All right. You have a good day, sir.
You too. Bye-bye.
All right, bye. Dude. It was awesome.